limits at infinity. This is different than infinite limits. In the section 1.5 where we talked about infinite limits, we're talking about vertical asymptotes. This is actually horizontal asymptotes. Let me write that here. So, for example, f of x equals 3x squared over x squared plus 1. If you were to graph that, you would see that you have a horizontal asymptote at, let me see, 3, at 3. So like this. And the graph kind of looks like this. And so the question is, what is the limit of f of x as x approaches infinity? This is what we mean by infinite limits, although rather limits at infinity. So as x approaches infinity, what is y getting closer and closer to? And that's that horizontal asymptote at 3. So the answer is an actual number when we talk about limits at infinity, versus what we did in the last section where we talked about things that said like the limit as x approaches 3 of f of x, and the answer was infinity or does not exist. That's a vertical asymptote, right? So as x approaches 3, what is y approaching? And the answer is does not exist, or the limit doesn't exist, so we say infinity. This we refer to as infinite limits. This is limits at infinity, and these are horizontal asymptotes. And you talk about this in pre-cal, and I'll remind you of some of the rules you learned in pre-cal. So there are basically 3 types of functions that you'll see, like the one here, where they have the same exponential value in the numerator and the denominator. So we're looking at the coefficients, 3 over 1, and that ends up being your horizontal asymptote. Okay, so here's an example here. Limit as x approaches infinity of 2x squared plus 5 over 3x squared plus 1. And so because they have the same exponential value, we just look at the coefficients, which in this case is 2/3, and I know that the horizontal asymptote is at 2/3. Therefore, as x approaches infinity, you're getting closer and closer to 2/3. Okay, so this is very simple because all you're doing is looking at the coefficients. On the next example, we have the limit as x approaches infinity of 2x plus 5 over 3x squared plus 1. And in this case, the exponential value is greater in the denominator than it is in the numerator. So when that happens, we just say that the limit is 0. In other words, the horizontal asymptote is going to be at 0. So again, you do this in pre-calculus, you look at horizontal asymptotes, and so that's basically what we're saying here. As x approaches infinity, y is getting closer and closer to the horizontal asymptote, which in this case is 0. Okay, so it's nothing more than what you did in pre-cal. And then the limit as x approaches infinity of 2x to the third plus 5 over 3x squared plus 1. In this case, you see that the exponent is greater in the numerator than in the denominator, and therefore the overall limit does not exist because there isn't a horizontal asymptote here. You are approaching infinity or negative infinity, so that depends. You'd have to plug in a couple of values here. So if you wanted to know, like, okay, you're not approaching a horizontal asymptote, but are you approaching infinity or negative infinity? You just have to plug in some values. So if you just wanted to know, of course you could put it on decimals, just plug in any number. So if I plugged 1 in to this function, which is easy to do, I would get 7/4. And then plug in another number like 10, and if you cube it, you get 1,000, so that'd be 2005, right, over, and plug in 10 here, that's 100, 301. So that's approximately 7, and this is approximately 1 point. So you can see that it's increasing. As x is increasing, y is increasing, therefore you're going to infinity. As x is increasing, y is increasing, so you're headed towards infinity. So the limit doesn't exist because there is no horizontal asymptote, but you could say infinity or negative infinity if you were asked. Okay, so you have three types, just to review. If the exponents are the same, you just look at the coefficients. If it's greater in the denominator, then the limit is 0, or the horizontal asymptote is 0. And if it's greater in the numerator, then it does not exist. Okay, so I think there was two more examples I wanted to show you. Let's look at the limit as x approaches infinity of 3x minus 2 over the square root of 2x squared plus 1. Once again, it doesn't look like they have the same exponential value, but they do, because the square root of x squared is just x. So these are both x's. So again, you're looking at the coefficients, which in this case is actually 3 over the square root of 2. And that's plus or minus. So in this case, you actually have two asymptotes, two horizontal asymptotes at 3 over the square root of 2, which is 1 point something, I think. So you're gonna have a situation that looks like this, and the function kind of approaches this asymptote, and then it comes up and approaches this one. So you have two horizontal asymptotes. So the limit as x approaches infinity is 3 over the square root of 2 and negative 3 over the square root of 2. And the last example, f of x equals x to the third power. The limit as x approaches infinity of x to the third is infinity. So we know that the graph of x to the third looks like this. So as x approaches infinity, y is also approaching infinity. So the overall limit doesn't exist, but we can say that it approaches infinity. And we could also say that the limit as x approaches negative infinity of x to the third is negative infinity, because as x is decreasing, so is y. So the overall limit doesn't exist, but we can say that it approaches infinity or negative infinity. And that is limits at infinity, horizontal asymptotes.